Hello. Today we'll place a satellite in a geosynchronous equatorial orbit, so the satellite appears to be stationary when viewed from Earth. We start this mission beginning at the point where the launch vehicle's rocket has burned out. We'll then enter a circular, low Earth parking orbit for about 2 hours to allow for equipment checkout before transferring to a circular, equatorial orbit. From there, we'll initiate a Hohmann transfer orbit, getting the satellite to the final geosynchronous orbit, with orbit period equal to 1 sidereal day. Start by clicking on the File tool from the menu bar and then selecting the default project option. This clears all existing orbits that you may have created. You can also do this using the Alt-D key sequence. Go to the Simulation Time Span text box and add 1 day to the simulation. Then press the Tab key and recalculate the orbit. Now, click on the Add Satellite button to see the Set Initial Parameters dialog. Choose the Burnout Above Earth option. Note that epoch is the same as the simulation start time. Do not change it. Assume that we have launched from Cape Canaveral, and burnout occurs slightly to the east. Use the mouse to click on this Earth location. When you do this, the proper GPS coordinates are placed in the corresponding text boxes. Next, enter 3,000 meters for the burnout altitude and 2,000 meters per second for the burnout velocity, pressing the Tab key between each entry. Finally, select 0 for the orbit inclination and press the Tab key. Note that the orbit inclination becomes 29 degrees rather than 0. That's because you cannot place a satellite directly into an orbit that has lower inclination than the satellite's initial latitude. That initial latitude is slightly less than 29 degrees. Now, click on the Set Parameters and Recalculate Orbit button. You should now see a partial orbit that is sometimes called a suborbit or ballistic trajectory. You may need to move your camera around Earth to see it. Next, go to the Satellite Group box and change the satellite image to Red Ball. Note that the default satellite name is Satellite 1. You could change it here, but leave it for now. While in this group box, also uncheck the Skytrack checkbox. Now go to the Display Group box and change spacecraft size to 3. Also, uncheck the following checkboxes: Sky Location, Star Labels, Satellite Orbit Steps, Satellite Ground Steps, Moon Orbit Steps, Moon Orbit Lines. Next, go to the Camera Group box and make the following changes. Change Looking At to Satellite 1. Change Viewing From to Not Controlled. Change Rotation Point to Satellite 1. Zoom out to see the results and then click on the Go to Apogee or Perigee button. Clicking here once takes the satellite to the highest point of the suborbit. Now we want to add a rocket burn that places the satellite into a circular parking orbit. To do this, go to the Satellite Group box and click on the Add Delta V button. You should now see the Delta V calculator dialog. From here, click on the Circularize Orbit button. This creates a circular orbit starting from where the satellite currently exists at the peak of the suborbit. Finally, click on the Use and Recalculate button. Assuming that your simulation time span is set to 1 day and 6 hours, you should now see several orbits with altitude equal to about 184 kilometers. Run the simulation and note that the ground lines are fixed to the surface of Earth, but the orbit lines are fixed in inertial space. Now, stop the simulation and return to the beginning. Next, click on the Go to Node button 4 times, moving the satellite from simulation start to the equator 2 hours and 39 minutes after burnout. This gives us about 2 orbits to do hardware checkout before firing the rocket. Note that the orbit has been drifting because of Earth bulge. While the satellite is at this node over the equator, go to the Satellite 1 group box and click on the Add Delta V button. In the Delta V calculator dialog box, type the number 0 in the inclination text box and then press the Tab key. Next, click on the Set Required Inclination button. Finally, click on the Use and Recalculate button. To return to the main window, you should now see the satellite in a circular low Earth equatorial orbit. The most efficient way to transfer from an orbit at one altitude to an orbit at another altitude is to use a Hohmann transfer orbit. First, we'll do a rocket burn to enter an elliptical orbit, assuming that our current position is perigee of this new transfer orbit. When we arrive at apogee of this transfer orbit, we'll do another burn to enter a circular orbit. If the apogee for this transfer orbit is 42,164 kilometers from the center of Earth, then our satellite will have an orbital period equal to 1 sidereal day, appearing stationary above Earth. Now go to simulation time equal to 3 hours and 15 minutes. If the timing for our first burn from low Earth orbit is correct, we can place the satellite over any longitudinal coordinate we want. There is a large ring of these satellites currently in orbit around Earth, serving communications, telecommunications, and weather observation purposes. Next, click on the Add Delta V button. When the Delta V calculator appears, note the elliptical orbit option. To make it easy for you, we've included a GSO button that places 42,164 kilometers in the apogee text box for you. Click on that button now, and then click on the Set Required Apogee for Elliptical Orbit button. Finally, click on the Use and Recalculate button to close this dialog and return to the main window. You should now see your elliptical transfer orbit. Change the size of the spacecraft to 30 so you can more easily see it. Now click on the Go to Apogee button until the spacecraft is at apogee of this elliptical orbit. The distance from the spacecraft to the center of Earth should now be about 42,000 kilometers. Next, click on the Add Delta V button again. From this apogee position, we want to enter a circular orbit. Therefore, in the Delta V calculator dialog, click on the Circularize Orbit button and then the Use and Recalculate button. The spacecraft is now in geosynchronous orbit, but only a portion of that orbit can be seen. Change the simulation speed to a larger value and run the simulation. Verify that the satellite settles over a particular longitude. To choose your own final longitude, you must change the timing for the Hohmann transfer burn accordingly. Note that each rocket burn, measured as a change in velocity, is recorded for you. You can use this value in the rocket equation, along with satellite mass, to calculate the rocket fuel mass required. Thank you for watching this video. We hope you enjoyed it. If you did, please give it a like and consider subscribing to the channel. We will be producing new content in the future. If you want to be notified when new videos are added, click on the notification bell. We need your feedback, so please leave a comment in the comments section. Goodbye.